So today I will discuss about the periodic table and the periodic properties of the elements. Now the necessity arises when there we observed a very large amount of elements and we have to study all these elements in a proper way. As because when I have to rule out a kingdom, I must have to know the territory in which I belong. So the chemists uh, were very eager to arrange all the elements in a proper way so that they can uh, memorize or they can collectively uh, study the all the properties of the elements in a proper way. So there are a large number of elements nowadays. It is about 118 elements, and it is almost impossible to know the all the properties of them separately. So we have to know the properties in a collection of the elements, and we have to find out the similarity between them. This is the main task of the chemist, to study the properties of the elements and arrange them at a regular way in a tabular manner so that they can study them easily. So this was the necessity of the periodic table, and the all the scientists were very eager to perform these with separate laws. First, Doverina tried this with his law of Chads, which states that the atomic weights of the middle element of each Chad is a very close to the arithmetic mean of those of the other two elements. Let us saw an example. Let us see a example. Lithium, whose atomic weight was 7, sodium, whose atomic weight was 23, and potassium, whose atomic weight was 39. If we check the mean, arithmetic mean of the lithium and potassium, then we get the atomic weight of sodium. But this was not so useful. Next, Lewland introduced his law of octaves, which states, according to the musical note, musical octave, sa, re, ga, ma, pa, dha, ni, sa. Like this way, the elements can also be arranged. Starting from lithium, according to this law, starting from lithium, there is a similarity observed in the elements sodium. So next, after 8 elements in potassium, also the same properties were observed. But this law, this law is also not so useful after certain periods. Then Mendel introduced his periodic law, which states that physical and chemical properties of elements are a periodic function of their atomic weights. So based on this law, Mendel arranged all the elements known at this time, all the elements in a tabular form, this like this one. Here the elements are arranged in the according to their atomic mass or atomic weight. Okay, but there was some problems or limitation in this table. What were these limitation? The isotope problem and some other reason. So so scientists get modified the law that give Mendel gave. So after modification, this law becomes some modern periodic law, which states that physical and chemical properties of the elements are a periodic function of their atomic number, not atomic weights. As because this is a simple logic, there is a simple logic behind it. As in the chemical reaction, the valence shell electrons or simply electrons are involved in chemical reaction, not and the total nuclear elements, that is the nucleus, in the nucleus that is a proton and neutron. These particles get intact among themselves and only the electrons get involved in the chemical reaction. So if we arrange the elements according to their atomic numbers, that is the number of proton or equal to the number of electron, then we get some limitation less table. In this table also there is a some contradiction regarding the position of hydrogen, but this is not so mandatory. The success of the table is far greater than the limitation. So this table is very important, and this table is nearly the correct one. Now in this table there is some properties. The elements are arranged according to their last cell electronic configuration in group wise and successively according to their atomic number. Now, according to the last cell electronic configuration, the elements are classified into some block elements. Like S block elements, the elements get entered to the last cell, that is S cell, and the general electronic configuration of S block elements is NS1 to 2. There is some properties. There are some many properties of S block elements. If we study them, then we can say that in case of these elements, all cells except the outermost one are completely filled with electrons. Except hydrogen and helium, all the elements are metal and highly reactive due to weak attractive force on the nucleus for the valence electron. Atoms of these elements can easily form monovalent or bivalent cation. That is, the ionization energy of the elements is very low due to high reactivity, and they do not occur freely in nature. Okay, there are some more properties of S block element. If we study, then we can say that all these are good reducing agents because of this low ionization potential. They are also good conductor of heat and electricity. They are also known as soft metals. They have low melting and boiling points and low density as compared to the adjacent transition elements. Cations of these elements cations of these elements are diamagnetic and colorless since orbitals do not contain odd electrons. Except beryllium and magnesium, S block elements impart specific color in flame test. Why? Because Bunsen burner, why the all the elements exhibit color? Because Bunsen burner of non-luminous flame rich in electrons. During the flame test, metal ions are converted to short-lived metallic neutral atoms by accepting electrons from the flame, and valence electrons of these neutral atom gets promoted to higher energy level. When the electron return to the lower energy levels, energy is emitted in the form of radiation of light of different way, like golden yellow for sodium, an orbital from 3s to 3p and back to 3s. Electrons from the orbital 3s gets promoted to 3p and return back to 3s. So golden yellow color emitted. And I say that beryllium and magnesium do not participate because ionization potential of beryllium and magnesium are very high because of smaller size, and their electrons cannot be executed to higher energy level. This is the reason behind it. So now we will discuss about some p block element. P block elements contain group 13, group 15, group 13, 14, 15, 16, 17 and 18. In all these groups, all the electrons get accommodated in p block element gets entered to the p block elements or p subshell. So these are collectively known as p block element. There, in this case, helium, although it is placed in group 18 element, group 18, this is not p block element because his its uh, electronic configuration is 1s2, that is the last electron gets entered to s subshell. So this is s block element. Now there are also some properties of p block element. If we uh, discuss them, then we can say most of the p block elements are non-metal, some are metals and few are metalloids and inert gases. The group 18 is in full of inert gases. On moving group 13 to 17, valence electrons are found to be more strongly held by the attractive force of the nucleus, resulting in a progress increase in ionization potential. Again, on moving down a group, due to gradual decrease in ionization potential, metallic character increases. Hence, metal exists at the bottom of the left side of the p block element, whereas non-metals lie at the top of the right hand side of the p block element, and metalloids stand midway between them. Most of them form covalent compounds, although although ionic character increases continuously down the group. Elements of this block non-conductor of heat and electricity, and and the electronegativity increases from group 13 to group 13 to group 14, 15, 16, 17 and 18. They exhibit variable oxidation state or valency, and the oxidation state is both positive and negative. And along group 13 to group 17, reducing power decreases and reducing power increases down the group from group 13, group 14, group 15, group 16, group 17 and etc. Now we are interested to some deal with d block elements where the last electron gets entered to the d subshell. Its general electronic configuration is n-1 d 1 to 10, ns 1 to 2. Now there is an important point here, that transition elements. What are transition elements? The elements in which the atoms in their ground state or in stable oxidation state contain incompletely filled d orbital. That is the general electronic configuration of transition elements is n-1 d 1 to 9. The d orbital is not fully filled up. So if we discuss the properties of d block elements, then we can say all the d block elements are metal and the ionization potential lies midway between s and p block elements. As because s block elements are highly electropositive in nature and p block elements are highly electronegative in nature, uh, the most d block elements exception is C3 plus, candium 3 plus, titanium 4 plus, and zinc 2 plus, copper plus. All are paramagnetic, and iron and cobalt are magnet which are ferromagnetic in nature. Now elements of group 5d, that is elements of group 5d, that is this uh, platinum, group 5d, that is platinum, gold and mercury. These are inert in nature under ordinary condition, so these are called noble metal. Now they also form colored ion in solids and also solid or solution, and also change in color of the formed ions, and they mostly form colored coordination complex This tendency may be described due to the small size of the atoms or ions and high nuclear charge of the ion and presence of incompletely filled d orbital capable of accepting electron from the ligands. So we have already discussed that these are less electropositive than S block element and more electropositive than P block element. And these many of them can form alloys. Okay. Now what is F block element? F block element may be defined as in which elements in which the last electron valence electron gets accommodated in F block, that is F subshell. The general electronic configuration is n minus 2 F1 to 14 n minus 1 D0 to 1 NS2. The characteristics of the F block elements are they are heavy metal, they exhibit variable oxidation state. Plus 3 is common and few are plus 2 and plus 4. Some member exhibit paramagnetism due to the incompletely filled F orbital or odd electron with odd electrons. They form complex compound, most of which are colored. They form they have high densities. They generally have high melting and boiling point. It is very difficult to separate them from a mixture because within each series properties of these elements are quite similar. As the properties of beryllium, uh, promethium, etc., etc., all these elements of 4F series, all these elements of the 4F series are similar to the lanthanoid. These are collectively known as lanthanide series. Lanthanum. These are known as lanthanide series. And as because the properties of thorium, palladium, uranium, neptunium, plutonium, etc., are similar to the actinide. These are known as actinide series. Okay, but in case of lanthanoid series and as well as actinide series, it is observed that with the increase in atomic number and ionic size, the size of the atom goes on decrease due to the decrease in ionic radii. This decrease can be explained with the help of screening effect of the f orbital. As f orbital are diffused in shape, the screening effect of f orbital are very low. So the nucleus can attract the f orbital electron towards it progressively from ceruleum to lutetium. So a steady decrease in atomic and ionic radii is observed. This decrease is known as lanthanoid contraction. Similar explanation is also applicable for actinide series. So this is known as actinide contraction. Next we are interested to deal with some properties which are observed in the periodic table. We would explain the definition also. What is atomic radius? Atomic radius may be defined as the distance from the center of the nucleus to the outermost shell containing the electrons is called atomic radius. Atomic radius are of three types: covalent radius, metallic radius, and van der Waals radius. What is covalent radius? It is defined as one half of the distance between the centers of two atoms of the same element bonded to a single covalent bond. What is metallic radius? Metallic radius is defined as the one half of the distance which is internuclear between the two adjacent atoms in metallic lattice. It should be mentioned here that metallic radius is greater than covalent radius. Next, we are interested to discuss van der Waals radiation. Van der Waals radius, the third type of atomic radius, which is defined as the half of the distance of the nuclei of two non-bonded neighboring atoms belonging to the same adjacent molecules of an element in the solid state. It should be mentioned here also that van der Waals radius greater than metallic radius greater than covalent radius. Now, as shown in the figure, atomic radius decreases as we goes from left to right in the periodic table. It has some simple explanation behind this. In case of atomic radius, the principal quantum shell remains unchanged in the same period. So the different electron enter the same shell, but due to increase in the number of proton, the positive charge in the nucleus also increases. So the attractive force of the nucleus for the electron in the outermost shell also increases. Hence, the atomic size, rather the atomic radii elements in the same period gradually decrease with the increase in atomic number. In any period, atomic size of the element of group 1 is maximum and that of halogen, that is the group 17, is minimum. In case of transition elements, such decrease in atomic size is relatively less. There is a differentiating there because there the differentiating electron gets into the penultimate n minus 1 d subshell instead of the outermost shell. The n minus 1 d subshell is closer to the nucleus. However, due to the port shaving effect of the additional d electron, there is a small increase of effective nuclear charge, and hence the decrease in the size with increase in atomic number is relatively small. Now, down the group atomic radius increases because a new electronic shell is added to each succeeding element to the number. Though the number of electrons in the outermost shell remains the same, this tend to increase the atomic size. At the same time, there is an increase in nuclear charge, which increase in atomic number, which uh, so the size decreases. However, the size should be decreased. But however, the effect of the increased nuclear charge is partly reduced by the shielding effect of the inner electronic shell. In practice, it is found that the effect of addition of new electronic shell is so large that that this outweighs the contractive effect of the increased nuclear charge, and hence there occurs a gradual increase in atomic radii on moving down the group. Next, we will discuss the variation of uh, ionization enthalpy. Now, what is ionization enthalpy? Ionization enthalpy may be defined as the ionization enthalpy can also be more accurately can also be said that fast ionization enthalpy. This can be defined as the amount of energy required to remove the most loosely bound electron from the valence shell of an isolated gaseous atom existing in its ground state so as to form a cation in the gaseous state. Now, here beryllium has the, if we consider the example, beryllium which has some electronic configuration 1s to 2s2, which has higher ionization enthalpy than boron 1s to 2s2 because ionization of beryllium requires removal of one electron from its completely filled 2s orbital in the valence shell. For similar reason, magnesium 1s to 2s2 has greater ionization enthalpy than aluminium 1s to 2s2 So this is ionization enthalpy. This is increases along the period because the size of the element decreases. As because the size of the elements decreases, so the nucleus attract the electrons more strongly towards it. So the necessary energy for removal uh, so the necessary energy for the removal of the electron is greater. So the ionization enthalpy increases along the period, and as the atomic radii down the group increases, so the ionization enthalpy decreases down the group because the force of attraction of the electron towards the of the nucleus towards the electron is relatively decreases. Now we will describe the electron gain enthalpy. What is electron gain enthalpy? Electron gain enthalpy may be defined as the enthalpy change involved when an electron is added to an isolated gaseous atom in its lowest energy state, that is ground state, to form a gaseous ion carrying unique negative charge. Electron gain enthalpy of chlorine. Here, a exceptional result is electron gain enthalpy of chlorine is unexpectedly greater than fluorine. The reason behind is that the electrostatic attractive force of nucleus favors the addition of an electron to the small size fluorine atom. The added electron, however, creates an unfavorable effect because of the electron-electron repulsion from the other electron in the small size 2p subshell. On the other hand, in chlorine atom, the added electron goes to large 3p subshell and experiences less electron-electron repulsion. Consequently, the numerical value of electron gain enthalpy of chlorine is greater than fluorine. Similar reason is also applicable for sulfur. The electron gain enthalpy of sulfur is greater than oxygen. This can also be explained with the help of similar reason. And we observe that halogen have the highest electron gain enthalpy. This is due to the fact that the valence electronic configuration of halogen is ns2np5, and so they require only one more electron to acquire the stable inert gas like electronic configuration ns2np6. As a result, halogen have a strong tendency to accept an electron, which implies the numerical value of electron gain enthalpy are very high. Now we will describe the term electronegativity. Electronegativity may be defined as the tendency of an atom to attract the shared pair of electrons towards its nucleus when the atom is covalently bounded with a molecule covalently bounded in a molecule. Consequently, more electronegative atom withdraws the bounding electron towards its own nucleus, giving rise to an accumulation of negative charge on it. Along the period, the electronegativity increases because as we move from left to right along a periodic table, nuclear charge increases while the atomic size or radius decreases. Hence, the attraction between the outer electron and the nucleus increases on increasing atomic number. Consequently, the electronegativity increases. So, the group 1a have the low electronegativity and group 7a has the highest electronegativity. As we move down the group, electronegativity decreases because of the increase in atomic size, atomic radius, as well as the magnitude of the nuclear charge increases down the group. But the effect of increased nuclear charge on the outer electron is mostly counterbalanced by the screening effect of larger number of inner electronic shell. As the nuclear pool on the outer electron decreases due to the increase of atomic size on moving down a group. Consequently, electronegativity of the atom decreases down the group. So these are all properties of the elements in the periodic table.